Everyone. So in this video, what we're going to do is, now that we know a little bit about congruences, we're going to rewrite the proof of Euclid's theorem, the fact that there are infinitely many prime numbers, using the language of congruences. So let's remember how the proof goes. So let's suppose for a contradiction that there are only finitely many prime numbers. So finitely many primes. And let's write them all down. There is P1, P2, ... up to Pn. Okay, and that's all of them. Okay, and then we consider a new number n, which is the product of all the primes, P1, P2 through Pn plus 1. Then n is, since n is larger than Pn, it is not prime because Pn is the largest prime, allegedly. So n is not prime. And but by the fundamental theorem of arithmetic, there's going to be a prime divisor of n. By the fundamental theorem of arithmetic, n does have a prime divisor. A prime divisor q, so that q divides n, or equivalently, in terms of congruences, what that says is that n is congruent to 0 mod q. But since q is a prime, it is one of the PIs. Since q is prime, and we have written all the primes there are, q has to be PI for some I, for some number I between 1 and n. And therefore, well, PI is 0 mod q, and n, which is P1 times P2 times PI times Pn plus 1, this will be congruent to, well, this is congruent to 0, so that product of primes is 0, so this is 1 modulo q, but that is a contradiction because we have that n is 0 mod q and n is 1 mod q. Since q is a prime bigger than 1, this cannot be. This is a contradiction. And therefore, the contradiction is with what? The contradiction is with the fact that there are infinitely many primes. So we assume that there were finitely many, so there must be infinitely many. Thus, there are infinitely many primes, as we wanted to show. Okay, so now what I want to do, now that I've explained this more or less using congruences, what I want to do is prove a particular case of Dirichlet's theorem on primes and arithmetic progressions. So let's do one very particular case, which is the following. There are infinitely many primes of the form 4n plus 3. So primes that are a multiple of 4 plus 3, i.e. Infinitely many primes P that are congruent to 3 modulo 4. Okay, so let's modify Euclid's proof to show this particular case. As I said, this is a case of a much larger theorem, which is Dirichlet's theorem on primes and arithmetic progressions. What this says is that there are infinitely many primes in the arithmetic progression for n plus 3. Okay, So let's show that. So again, using contradiction, suppose there are only finitely many primes or that are finitely many primes that are congruent to 3 mod 4. Okay, and let's name them all. So there is some P1, P2, P3, etc., up to some Pn, and those are all the numbers such that Pi are primes, and each Pi is 3 mod 4. And now consider n, our new n. What I want now is a number that is 3 mod 4. So 4 times P1 times P2 times Pn minus 1. And note that n is congruent to, since this is 0 mod 4, n is congruent to minus 1 mod 4, which is the same as 3 mod 4. Okay. Now, by the fundamental theorem of arithmetic, n itself has a prime factorization. By FTA, n has a prime factorization q1, q2 through qr for some primes qi. And notice that n itself is 3 mod 4, and 2 does not divide n because n is 3 mod 4. If 2 divided n, then it would be either 0 or 2 mod 4. So it is none of those primes is the prime 2. So they are all primes that are not 2. And also notice that a prime, each one of those QIs is either 0, 1, 2, or 3 mod 4 by the fact that every number has a remainder of 0, 1, or 2 or 3 mod 4. And it is not, since QI is prime and QI is not 2, it cannot be 0 or 2. So each QI has to be 1 or 3 mod 4. Now, I'm going to claim that there is at least one of those QIs has to be 3 mod 4. If all of them, if all the QIs were 1 mod 4, then what would happen? It would happen that n, which is the product of all these QIs, by the properties of congruences, that would be, well, 1 times 1 times 1, which is congruent to 1 times 1 times 1 is congruent to 1 mod 4. But n is congruent to 3 mod 4. So there is one QI that is 3 mod 4. Because if they were all 1 mod 4, then the product would be 1 mod 4, but the product, we know it's n, is 3 mod 4. So there's at least one that is 3 mod 4. But since this is a prime and it is 3 mod 4, it has to be one of the ones above. It has to be one of the PIs. Okay, so then it is prime, it is 3 mod 4, so QI is some PJ for some J between 1 and n, right? But then what happens? Well, QI divides n, so n is 0 mod QI, so n is 0 mod PJ, But also from this expression, we know that n has to be, well, you see this is pj is going to be one of these, so this has to be 0. This is 0 mod 4. This is 0 more pj for any of those j's. So n would be 0 minus 1 modulo pj, which is minus 1 modulo pj. So it is at the same time 0 modulo pj, and it is also minus 1 modulo pj, and pj is larger than 2, so this is a contradiction. This is the contradiction we were looking for, and therefore, thus, there are infinitely many primes that are 3 mod 4. Because that was our assumption. The contradiction is with the fact that we assumed that there were only finitely many primes that are 3 mod 4. As I said, this is one special case of a much larger theorem, which we are not going to prove in this class, but which is very important. There's Dirichlet's theorem on primes in arithmetic progressions, which says that so if a and m are integers with m bigger than 1, and the GCD of a and m equal to 1, then there are infinitely many primes, and the arithmetic progression which is given by a plus km with k bigger or equal to 0. There are infinitely many primes in that progression, and equivalently, infinitely many primes. There are infinitely many primes of the form a plus km, or equivalently, there are infinitely many primes of the form congruent to a modulo m. Okay, and this is what we just proved was precisely that. We just proved there are infinitely many primes that are 3 modulo 4. But this says there are infinitely many primes that are 1 mod 4. This says there are infinitely many primes that are 1 mod 3, or 2 mod 3, or 5 mod 7, but not, of course, infinitely many primes that are, for example, 2 mod 6, because those would be primes that are even, and there's only the prime number 2. Okay, so using the same trick that we just did, using this same trick, you can prove some other cases. You can prove, for example, that there are infinitely many primes that are 2 modulo 3, or infinitely many primes that are 5 modulo 6. But this trick sort of breaks down after that, because there are more cases for these kind of products, and then the proof doesn't work. So you need something more advanced to prove Dirichlet's theorem in complete generality. Okay, so that was all I wanted to say today. Thank you.